Hi everyone, welcome back to the Heterogeneous Parallel Programming class. Welcome to the fourth week of the class. And starting this week, we're going to introduce more advanced parallel computation patterns. And in the process, we're also going to work to increase the level of your parallel programming skills. And for lecture 4.1, we are going to introduce the second major parallel computation pattern, reduction. The objective of this lecture is for you to learn the parallel reduction pattern. And this is a very important class of parallel computation. And we're also going to be using this pattern to introduce the concept of work efficiency analysis and resource efficiency analysis. The use of reduction usually comes from a strategy called partition and summarize. And this is a very commonly used strategy for processing very large input data sets. And in order to apply this strategy, there needs to be no required order of processing these elements in the data set. And in mathematical terms, this is called associativity and commutativity. So associativity means that if we process multiple elements, let's say three data elements, A, B, and C, it doesn't matter whether we process AB first and then process the result of AB with C, or we process the BC first and process the result of BC with A. So this gives us the flexibility of processing some subset of data ahead of others. And the other one is the commutativity, and that means that whenever we have an operator, let's say addition, and when we say A plus B, it's the same as B plus A. And this would not be the case for subtraction. So whenever we have an operation that we need to do on a large data set, and the operation that we're doing is both associative and commutative, then we can apply this partition and summarize strategy. When we apply the strategy, we'll first partition the data set into the smaller chunks. And then we have every thread to process a chunk. And in the end, we would generate results for all these chunks. And we use a reduction tree to summarize the results from the chunks into the final answer. So the reduction is going to be the critical step in the end to be able to assemble all the partial results into the final result. For those of you who are familiar with Google and Hadoop MapReduce frameworks, these two frameworks support exactly this kind of strategy, and it's commonly referred to as MapReduce in certain communities. We will focus on the reduction tree step for now in this lecture. Reduction is also used in some other circumstances. And in this particular case, we often will see reduction will be used to enable other parallel programming techniques. And for example, we can have a situation where we have multiple threads that are processing the data, and they need to write into a common output location. And as well as learn more about this kind of common output location, it's going to create a serialization of the write process into this location. So a very common strategy is called privatization. And this privatization technique essentially replicates the output location into many locations so that each thread has a private output location. And every thread will be writing into that private location during the computation. And after all the threads completed their work, then we use a reduction tree to combine the values of the private locations into the original output location and therefore generate the final result. So this is a technique that is not in the original computation per se, but it's actually used to enable a particular way of reorganizing your parallel computation for better efficiency, and then use the reduction to clean up sort of the side effect of that transformation, so that you can assemble the final result correctly. So now let's introduce reduction computation. And mathematically, a reduction computation is a computation that summarizes a set of input values into one value, and using what we call the reduction operation. And there are many types of reduction operations we can have. For example, we can have a max reduction operation. Essentially, a max reduction operation is to determine between two elements, the bigger one of the two. So whenever we have a max reduction on a large data set, essentially we're finding the maximal value of the entire data set. And so that will be the single answer out of that data set. Min is the opposite of max, where if we apply that to two data values, it will find the smaller value of the two. But whenever we apply a mean reduction to a large data set, we're finding the minimal value of that data set. Sum is another possible reduction operation. And when we apply sum to two values, that means that we're adding the value together to get that single answer. But if we apply sum reduction to a large data set, that means that we're adding all the values together into a single sum, and that will be the answer of the reduction computation. And product is the multiplication version. So essentially, if we apply product reduction to a large data set, it will give us the total product of all the data elements. And all these operators, as you can see, are both associative and commutative. So that's why we can use the reduction on each of these kind of operations. And reduction is oftentimes also used with user-defined reduction operation function. So the user often can just provide an operation that is equivalent to one of these max, min, sum, or product, but it may be just whatever the user wants to do with these data values. And but in order to use a reduction, user-defined operation on a reduction computation, the operation must be associative and commutative. And it also needs to have a well-defined identity value. That is, a value, when operated with another value, the answer is always the other value. So, for example, sum 0 is an identity value for sum, because when we add 0 with another value, the outcome is always that other value. And if we have a max reduction, the identity value is the smallest value possible for that data set, so that whenever we try to find the max value between this smallest value and another value, the answer is going to be always the other value. The reduction computation is oftentimes referred to as an example of collective operation. For those of you who are familiar with the MPI or message passing interface, terminology. So this demonstrates that it's widely used in all kinds of parallel computation, not just in let's say CPU or GPU, multi-core CPU or GPU computation. It also is widely used in massively parallel, cluster computation as well. So we can write a fairly efficient sequential reduction program by following this procedure. We can initialize the result as an identity value for the reduction operation. So if we are doing a sum reduction, we can just initialize the value to be 0, as we mentioned before. So it could be the smallest possible value for max reduction, the largest possible value for the data set for the min reduction, and 1 if we do a product reduction on that data set. And once we initialize the result, then we can iterate through all the input. We can visit each input value in an iterative manner. every time we visit an input value, we will do a reduction operation on the current result value and the operation and the new the input, and we would write the result into the result value. So we update that result value for by visiting each input data. So every time, let's say we visit a new value, we will compare the current result value and the new value for the max reduction. And then if the current value is bigger than the result value, then the current that input becomes the current result, becomes the result value. So as we visit all the input values, we keep updating that result value. And after n steps, we finish visiting all the input elements. Then the result is the final answer. So this is a very efficient sequential algorithm because we only need to process every data value once. So this is a linear algorithm. The computation time is proportional to the size of the data, and is this as efficient as it gets. And so any parallel computation will be compared against this linear algorithm because if we add more work during parallel computation, then the performance will be penalized by those extra work. So any performance enhancement that we can have for parallel computation will have to be able to compensate for those extra work that we introduce in order to do this computation in parallel. Now we are in the position of introducing parallel reduction tree algorithms. And this graph shows the concept of parallel reduction trees. And it basically, all the parallel algorithms that we will be introducing are based on this same concept. So in order to perform a reduction computation in parallel, we will take multiple steps. And in the first step, we will apply the reduction operator on all pairs of input data. So let's say if we have 8 elements in our input data, we're going to do the reduction operation on 4 pairs. 8 elements will be organized into 2 pairs, and then we'll do the reduction operation on each pair. So in this case, if we do a max reduction, 3 and 1, the max value is 3, and 7 and 0, the max value is 7, and so on. So after the first step, we have reduced the amount of data in half. And then we can do the next iteration. We can do the reduction operation to 2 of these intermediate results. So now we can compare 3 and 7, and then the max value between this pair is going to be 7. And we do the same thing for 4 and 6, and we get 6 there. And finally, we have the final step where we compare the last two intermediate results. And these intermediate results represent the maximum of this half of the data set and the maximum of the second half of the data set. And here, of course, the value is going to be 7. So we have the final answer. So if we look at this, we have a lot more parallelism going on. In the first step, we have 4 parallel reduction operations going on in parallel. And then we have fewer number of parallel operations. We have 2, and then eventually we have 1. Obviously, if we have a larger amount of data, then the number of parallel operations in the first step will be bigger. It's half of the number of data elements. So by processing a large data set, we typically will use a large number of threads to be able to do this in good speed. And as you can see, in this particular example, when we have 8 data elements, we're doing 4 operations plus 2 operations plus 1, so that's 7 operations. So we actually need to perform n-1 operations for the reduction. So this maintains the linear algorithm complexity when we do the parallel computation, and the number of operations is truly comparable to the sequential algorithm. So this is an example of a work efficient parallel algorithm. And the other observation is the number of steps that we will take for the parallel computation is typically log base 2 of n, because if we have 8 elements, we're going to have 3 steps. Essentially, every step will reduce the amount of data by half. So in log n steps, we will be able to reduce the amount of data to 1, and that's the terminating condition. So if we have any arbitrary n elements, we can apply log base 2 to that number, and we'll get the number of steps that we need to take in this parallel computation. If we have unlimited resource, the number of parallel steps determine the execution time. So by applying a lot of hardware execution resources to this problem, we can speed up the execution. Instead of doing 8 steps in the sequential algorithm, now we can do 3 steps and finish the computation faster. Reduction is oftentimes done in real life, other than computation. So, for example, any tournament is essentially a reduction tree with max operation. Here we show a kind of a picture of the semifinals and the finals of the last World Cup in South Africa. So we have 8 teams coming into this tournament, essentially the semifinals, and then we have in the first round we have 2 teams playing against each other. So that's the first step in the previous slide, equivalent to the previous slide here, where we have 2 teams playing against each other to be able to to get a winner between these 2 teams. And then we have the winners of each pair to play against each other. And then finally, we get the semifinalist, and then we have the winner of these 4 teams to play against the winner of the other 4 teams, and that's the final game. So if we look at this picture, we will realize that this is just a more artful rendering of a reduction algorithm, based on 8 data elements. So we see this kind of process in many real life situations. It's not just confined to the computation field. So let's do a very quick analysis of that parallel algorithm. So for n inputs, the reduction tree performs in the first step half n number of operations, because we're doing them on a pairwise basis. And after that step, we have half the number of data values remaining. So we only need to do 1/4 of the original n operations for the second step, and then 1/8 n operations in the next step until we reach n. So this gives us essentially a expression that we can add up to n-1. So this gives us the total number of operations. And just to give you a kind of intuition about the resource efficiency and the parallelism of this kind of algorithm, let's say if we have 1 million input values, and if we take log base 2 of 1 million, we get 20. And so this tells us that if we have unlimited amount of resource, we can actually get a reduction value out of 1 million elements in just 20 steps. And this is a very, very good a deal. So this is the reason why all these tournaments use the reduction tree, because this allows us to have a very small number of steps to get a champion out of many, many teams. And then we need to assume that we have enough execution resources. And when we calculate the amount of average parallelism that we can get out of this, we take the total number of operations we need to perform, which is n-1, and we divide it by the number of steps. So it gives us the average number of parallel operations at each step, and the number of steps is log n. So if we take that 1 million element example, and then we divide it by 20 steps, we see that the average parallelism is 50,000. This is very impressive. However, it comes with a very steep cost. The peak resource requirement is actually 500,000 or 500,000. So that means that in order to be able to do this computation in 20 steps, we need to provide 500,000 execution units in that first step. However, the amount of required resources will decrease very quickly. So we will be essentially reserving a very large amount of execution resource, but then towards the end of the computation, we'll be using only a very small portion of the resource. So this algorithm is definitely not resource efficient. And this is the reason why when we have very large tournaments, typically we will have the first several rounds of the games spread out in more of the even the neighboring cities and so on, because it requires a large amount of resource in order to get all these early games. And then once we whittle down the number of teams, then we can bring all these teams into one place and then do the next couple rounds to determine the champion. So this is a very important consideration as we look at the parallel algorithms moving forward. That is, what is the resource efficiency of these parallel algorithms? Are we going to be using a whole lot of resources at some phases of the execution and then idle most of those resources and only use a small portion of those resources at most of these other steps? So the other important analysis, as we already kind of alluded to, is the work efficiency analysis. So this particular algorithm, style of algorithm is work efficient because the amount of work done is comparable to a efficient sequential algorithm that it has linear algorithm complexity. However, many parallel algorithms are not work efficient, and we will actually introduce some of these work inefficient algorithms in the next few lectures. So this concludes our lecture here. And if you are interested in learning more about the nature of the reduction computation and sort of the design of a simple parallel algorithm for reduction, I'd like to encourage you to read section 6.1 of the textbook. Thank you.